Welcome to lecture number 8 for ECE 376 Embedded Systems, MLAB8 and C Programming. Now, there's step-by-step instructions for how to compile and download a program using MLAB8 and PIC18. Those are on Bison Academy. The video here, I'm going to kind of demonstrate how you download code and how you compile your C code. Also, if you're not terribly familiar with C, or you forgot most of what you learned in the Introduction to C Programming, don't worry. We start with fairly simple C programs and build from there. And also, quite a few of the features that are available in C we don't use, mainly because our little processor only has 64K program memory. If you get too elaborate with inheritances and objects, it takes up too much space. So we're just going to use the basic C programming. What C does, it offers things like multiply, which is actually a big deal. You can divide. I have arrays, things like that. C coding is actually a whole lot easier than assembly. But we made you start in assembly just so that you suffer like everyone else and realize how powerful and how painful assembly is. Likewise, there's a reason that industry tries to shy away from assembly. Also, if you want to get an A or B in the course, please do the homework and tests on your own PIC board. Writing the programs on paper or copying someone else's code really isn't that much fun. It's sort of like weightlifting. Watching someone else lift weights doesn't really do much for you. You got to do it yourself. So likewise, the fun part of this class is writing your code, downloading it, and see it actually working. So definitely do try to write your own code and make sure it works. If your PIC board doesn't work, let me know and I'll fix it for you. I've got spares too. So let's start out. What C coding is. The lowest level of programming is machine code. That's what computers used back in pre-1950. It's extremely cryptic, hard to understand, hard to debug, but this is how computers operate. This is a program on the PIC board. Looking at it, you have no idea what it is, but that's what the program looks like. What we started the course in was assembly. Assembly is much superior to machine code. It's sort of meaningful names that represent valid machine operations. It's fast, it's efficient, but the instruction set is very limited, and you get exceedingly cryptic code that's hard to debug, hard to maintain. It's what I call throwaway code. If you're given someone else's assembler, it's almost easier throwing it away and starting over. For example, the same code that we had before, this code right here, in assembly looks like this. Now you have a shot at figuring out what's happening. I'm clearing tris C, makes port C output, clearing port C, and counting. C is way better than assembly. What C does, it has exciting things like multiply. I can divide. I can do arrays, for next loops, do loops, if statements. In C, you can write code which is understandable, testable, and reusable. That's the whole reason for using C. I want to write a code that's reusable. I don't want to have to start over all the time. C allows you to do that. You can also write C code which is completely cryptic if you really want to. That's not really the point behind C. Try to write code which is understandable. Now the procedure for writing and compiling a C program, that's all here. It's also on the lecture notes on Bison Academy. I'm going to go demonstrate it for you. So to start out, just like we did in assembly, I do project wizard. Then I tell the processor, still at PIC18F 4620. Now when I get to the language, this is where it changes. We were using assembler. Now we're going to use the high-tech C compiler. So these are all the different compilers we have in here. What you want is this one, the high-tech Universal Tool Suite. If that doesn't show up on your board, you need to install the high-tech C compiler. It's a free C compiler that you can use. It's buried in their menus. Shoot me an email if you're looking for it, and I'll point you to where to find it. There's also a couple of different versions. We're using the free student version. What the free version does is it throws a bunch of extra no-ops in your code to slow it down. For $500, they'll take out the no-ops. We have no problem with speed in this class, so use the free version. Once you get the C compiler, it's pick your favorite directory. Here, I created a bunch of subdirectories. This is for lecture number 8. That'll be my subdirectory, and pick your favorite name. I like the name Jake, kind of inspires the masses, or C Programming. Pick the file that you want. I'm going to be using 1234.c. Otherwise, you can go on Bison Academy and download a code. And what you wind up with is something that looks like this. This is the project I'm compiling. This is the program that's inside the project. Everything's a project in MLAB, so if this is empty, I'm not compiling anything. It doesn't care what I'm editing. When I compile, it's the project that compiles. You need to offset your code. Again, there's a bootloader on here that takes up the low 800 spots in memory. So that goes under right here. Project, build options, project, code offset, 800. And I'll show that to you again. It's under project, build options, project, linker, offset by 800. If your code worked yesterday but doesn't work today, you forgot to offset your code. Once you do that, you've got your C program. It's similar to assembly. I need this include pic18.h. Things like tris-A, tris-B, tris-C, that's not a standard C instruction. That's very specific to this processor. This gives it a compiler directives that tells it what is tris-A, tris-B, tris-C. Easier than assembly, to make all pins output, just make it a 0. All pins are binary, and I just want to write the number 1, 2, 3, 4 to port A, B, C, D. This right here is the stop statement. It's while 1. 0 is false, anything non-0 is true. This will just sit there and stop at that line of code. To compile, you do project build all, or F10. And hopefully you get a success. What this tells you is your code compiled into 58 bytes. It's 2 bytes per instruction, so it's compiled into 29 lines of assembly. If I open up a couple different files, let's open up the .list file. This tells you how your code compiled. These are all the different variables. That's the pic18.h. Here's the start of my program. I'm going to say, let's see, tris-B equals 0. That compiled into the following assembler. Move 0 to W, move W to address 3987. That's where tris-B is located. Tris-C equals 0. Move 0 to W, move W to address 3988. That's where tris-C is located. This is the reason we like C. It compiles to assembly very efficiently. Each line of C compiles into a couple lines of assembly. If I look at file open, let's see, the hex file, that's your program. That's what the PIC board wants. Once you compile your code, again, this compiler is actually semi-friendly. If there's a mistake in your code like this, and I try to compile it, it's going to come back with an error. Double click on it. It says, I don't know what to do with this line of code. Fix that line of code. And you now have your hex file. The hex file is what I want. Now go into the super amazing awesomeness graphic user interface by Nate Zimmerman. Connect to your serial port, select your file. Again, it's the name of the project, not the name of the file. This is cprogram.hex. Another way to check, it's currently 3:26 p.m. on July 14th. This is just appeared. That's the correct file. So I'll select that guy. Open. Hit the reset button. Gives you that 321 message. And program. And voila, you've got the number 1, 2, 3, 4. Okay, so that's compiling and downloading code. Kind of walks through all that. I'd like to give you a little bit of a taste of why we like C. Let's just modify the previous code. Instead of displaying 1, 2, 3, 4, let's count. I'm going to have a long integer, a 32-bit number of I. that's going to count. Send the low 8 bits to port D, next 8 bits to port to port C, then B, then A. If I compile, that's F10. It'll compile the code, and right here, see, that was 278 lines, or 278 bytes, 139 lines of assembly. Once I compile it, I can now download the code, hit reset, program, and poof, I've got a new program on there. This one is counting, so port D is the low 8 bits, port C is the next 8 bits, port B is the next 8 bits, the high 8 bits. I now have a 32-bit counter in C. Go over to source file and add in the shift.c. Clear out the old one. This is another one that's kind of pretty. It makes the lights blink back and forth. I'm again going to have a 32-bit counter. For 31 times, I'll shift it left by 1. Then I'll shift it right by 1. What that does is compile. That was 562 bytes, 281 lines of assembly. Go over to the super awesomeness code for downloading it. Send that hex file. And this is what it looks like. The little light just blinks back and forth. Way easier than C than assembly. That's why we like C. Again, if you're worried about your skills with C programming, again, don't worry too much about it. The main things you need are if statements, if then else, do, while, subroutines, and that's about it. A lot of the other fancy features we don't necessarily need. Kind of what I found is you can do anything with an if statement. May not be stylish, but it works. A couple definitions, as well as a little bit of review of C programming. In C, you have to declare your variables before you use them. That tells the compiler, is my variable a single byte, 2 bytes, 4 bytes, 8 bytes, 10 bytes? It also has to tell if I see a number like 255, is that plus 255 or minus 1, 2's complement. So you have to declare them character or unsigned character. The difference is if you use an if statement, if x is greater than 0, depends whether it's signed or unsigned. In C, you've got addition, subtraction, multiplication, that's a biggie, division. There's also modulus. We do this for things like rolling dice or creating random numbers. 5 mod 2 is 5 divided by 2, take the remainder. Plus plus is auto increment, minus minus auto decrement. Logical AND is an ampersand. Logical OR is a vertical. Logical exclusive OR is raised to the power. Shift right and shift left. You can use, when you define your variables in C, I can define a variable, I can define it and initialize it, I can define a couple variables at once, I can use arrays. Just don't go overboard with the array. You only have 3692 bytes of RAM, so you can quickly run out of memory if you have large arrays. You can do conditional expressions. Exclamation means not. 0 is false, anything non-zero is true. Not port B is the complement of port B. Single equals is assign, double equals is test. This really bites a lot of people. If I say RB0 equals 1, a single equals, that assigns 1 to RB0. Anything that 0 is false, non-zero is true, so this is always true. If I use a double equals, that says compare RB0 to 1. If it's equal to 1, do the following, not equal to 1, skip. That's really hard to find in your code. If you have a problem with your coding, check for that single equals or double equals. That's a really common mistake that people make. It's hard to find. There's also if statements. Again, you can do almost anything with an if statement. This says, if the button is pushed, increment port C. There's if then else. I could say, if I push the bar B0, increment port C, otherwise decrement port C. There's while loops. If I do while 1, 0 is false, 1 is always true. while one says do the following forever and ever. That's actually really common. In embedded systems, you typically have a loop that runs over and over again. For example, if I build a stoplight, I want the stoplight to work over and over again. I don't want it to work just once. So there's almost always an infinite loop in your code. Sometimes you'll have a while loop, so do the following, like while the button's being pushed. A do loop says do the following and then check. A for loop is typically like for I equals 1 to 10, do the following group of statements 10 times. And an infinite loop, like I mentioned. Another nice thing about C is you can do subroutines. If I have int square of int, what that means is this is a subroutine called square. I can use it elsewhere in the code. I can call it from 5 different spots. If 5 different spots call it, I don't need 5 copies of the subroutine. Just 1 copy is all I need. And each of those other 5 spots can call the same routine. What the subroutine does is I pass it a 16-bit number called data. When I'm done, I return a 16-bit number. And the thing that gets returned is right here. The last statement is typically return. It says end the subroutine and return to the calling routine a 16-bit number called result. For example, this one I'm going to pass the information in data, square it, and return the squared answer. So this is the square of x. In C also, it helps if you have a standard structure. This is really a convenience for the next person. When you work in industry and you get promoted, the poor person has to pick up where you left off. It will really help him or her if you have a label block saying who wrote this code, when it was written, how to get a hold of you, your global variables, your subroutines, and then the main routine. If you have everything in the same order, it helps follow the code and see what's happening. Also in C, you have to declare your variables before you use them. So in C, the subroutine names go before the main routine. Also, for C versus assembler, we've been looking at assembler. Assembler is very fast, very efficient, but really hard to use. But the reason we use C is it compiles very efficiently into assembler. The compiler claims it's 80% efficient, and like most manufacturers, they lie. If you compile your C code, you're going to find out it's about 3 to 10 times larger than assembly. That's fairly typical. Every time you go up a level, the code size increases 3 to 10 times, execution is 3 to 10 times slower. So assembler to C, the code's going to go up 3 to 10 times. If I go C to an interpretive language like MATLAB, they'll be another 3 to 10 times larger. Go level up to some artificial intelligence language, be 3 to 10 times slower. If I really want speed, I go to the lowest level, that's assembly. One level up from assembly is C. That's kind of why electrical engineers tend to use C a lot. It compiles very efficiently. To kind of see that, let's take the old program we had before. This sends the numbers 1, 2, 3, 4 to port A through D in assembly. In assembly, that took 16 instructions. In C, when I compiled it, it turned into 29 instructions. You get like 1.8 times larger. You can tell that by when I compile it, I get this message. And this guy right here says my code is 58 bytes. 2 bytes is one instruction. So it's actually 29 instructions in a C, in assembly. Take a second example. This is a 32-bit counter. Here's the assembly code. In C, this is one way to do it. I'll define a 32-bit number called x. I'll increment x and then send the low 8 bits to port D, the next 8 bits to port C, the next 8 bits to port B, and so on. This is kind of standard in C. I've got a 32-bit number being written to an 8-bit variable. The way it does that is it takes the least significant 8 bits, sends it to port D, lose everything else. So this sends the lowest 8 bits to port D. Now shift it right. That's what that double greater than means. Shift it right 8 times, take the result, put it in port C. Shift it right 16 times, put the result in port B. This is 67 lines, or about 4.5 times bigger. You can do inline assembly. Sometimes, well, normally you really want to avoid assembly. It's hard to maintain, hard to debug, hard to understand. Otherwise, it's great. Sometimes you really have no choice. If I really need speed, write it in assembly. If I write my code in C and it just doesn't fit, I have to squeeze it down. I can rewrite it in assembly. If I have a real-time processor and every 10 milliseconds it's got to run through the routine, I write it in C, compile it, and it turns out it takes 11 milliseconds. That's not going to work. I need to squeeze down the code in speed. So what you do is find out which routine is being called the most, handwrite those in assembly. That'll speed it up. Try to squeeze it down so it fits in that 10 millisecond window. Sometimes you have no choice but to write your code in assembly. It's really frowned upon. It's really not desirable, but sometimes you got to do it. If you have inline assembly, that's actually really easy on the compiler. It says I don't have to convert the following code to assembly. It already is assembly. So it's actually really easy on the compiler. It just makes it really hard on the next person who takes your code and tries to figure out what the heck you're doing. And finally, at the end of the lecture notes, there's a list of all the C variables. This is non-standard C. This is specific to the PIC 18F4620. When you do the include PIC18.h, this is what it includes. It includes compiler directives to say that port A is address 0F80. That's basically where port A is located. I can also address the bits. RA5 is bit 5 of port A. C is case sensitive and it's spelling sensitive. If you want to figure out how do you spell the name of this bit, it's TRISB4. So that's kind of what this is for. With that kind of gives you a little bit of background on using C with on your PIC processor. We're going to be using C from now on, because with C, you can actually do a whole lot more than we could before.